Okay, so now we have learned everything we need to know about simple harmonic motion, and we have all the necessary tools. Then we can start solving problems that involve simple harmonic motion. So we're going to start with a simple case now. Imagine a particle m, or just a mass m, attached to a fixed point on a horizontal wall by a spring. The spring has a spring constant k. So what happens, practically when you make a small displacement, it will oscillate, right? So this mass is kept on a smooth flow. That means no friction is applied onto this mass. Now, when we are asked to show that the mass moves with simple harmonic motion, in questions you get, especially for the A-level exam, you are asked to show that the particles moves with simple harmonic motion. That's the first thing you do. So when you do that, you just make a sketch of the original diagram. Then just make another sketch showing when the particle is experiencing a force, right? That means under tension, a situation where the particle is under tension. So that means this is the natural length L. This is the natural length of the spring. So when you displace the particle by a small displacement x, you know that the spring will be under tension. So there will be tension here, tension or force. Now this is a mass, so you have mg. Now this force is not influencing any motion in the horizontal direction. Now let's put F equal ma. If we put F equal ma, in this direction, right? So if it is at a displacement x, now what we do is we're gonna displace this mass by a small amount x, then we just replace it. Sorry, release it. So when you release it, the starting velocity is 0. So please keep that in mind. F equal a. When this is x, there should be an acceleration in this direction, x double dot. So F, the force, the only force acting is the tension, that is minus kx. Spring constant is k and the displacement is x. The force applied by the spring is obtained by the Hooke's law. This is the Hooke's law, kx. This negative sign is there because the force is in this direction. Equal m. A is now x double dot. Right. It's very simple. So now x double dot is equal to minus k over m times x. So this is quite like minus omega squared x. Right. So where omega squared is equal to k over m. Right. So this is the characteristic equation. It's a characteristic equation where omega squared is k over m. So we have proved that this particle will move with simple harmonic motion when displaced by a small amount x. Now we have figured out omega. So now we have to find the amplitude of this simple harmonic motion. For the amplitude we use v squared omega squared a squared minus x squared. So we know that obviously when it is released from rest, then this position would be the amplitude. That means x should be the amplitude in this case. So velocity is 0, omega squared a squared minus x squared. Now this implies a equals x. So this small displacement x is also the amplitude in this case. Now in a problem this x will be given. X will be given. Right, then the period. To find the period, t equals 2 pi over omega. So what is omega? omega is square root of k over m. So 2 pi square root of k over m is equal to 2 pi m over k. Square root of m over k. See how easy this is.